The equation for the capacitance of a parallel plate capacitor is C equals epsilon naught times A over D, where A is the area of either plate and D is the distance between the two. The equation for the capacitance of a spherical capacitor is C equals 4 pi epsilon naught times the product of the inner and outer radius divided by the difference between those radii. What's the equation for the capacitance of a cylindrical capacitor? Well, let's take the same steps that we applied in the previous derivations and apply it to the cylindrical capacitor shown in this diagram. So when I say the steps we applied previously, it goes something like this. Use Gauss's law. Maybe in some cases we'd have to use brute force method, but use Gauss's law to determine an expression for the electric field as some function of distance from the center. Then use the definition for potential difference as being a line integral. And lastly, use the definition of capacitance as charge divided by voltage, or better yet, capacitance is equal to charge times the inverse of the voltage. So step 1, use Gauss's law. Let's find what the electric field is in the region between the two conductors. So we'll say perhaps the inner conductor is connected to a positive terminal and the outer conductor to the negative terminal. Then the electric field can be found by making a cylindrical shaped Gaussian surface, and we'll say the length of our Gaussian surface is L and the radius is R. The radius of our inner conductor is A, and the radius of our outer conductor is B. Gauss's law tells us that the total flux, E dot dA, is equal to the amount of charge inside the Gaussian surface divided by epsilon naught. Now the amount of charge in this Gaussian surface is represented by this shaded region. We'll say that shaded region has a charge density lambda. So we get E times 2 pi r times L is equal to lambda times L divided by epsilon naught. The L cancels out, and we have E is equal to 1 over 2 pi epsilon naught times lambda over r. So now we want to know what's the potential difference from point A to point B integrating along this path. So step 2, the potential difference is equal to the integral from r equals A to r equals B. Well, I guess negative the integral if we want to be technically correct, but we're only interested in magnitude in a derivation of this sort. And take all the constants out of the integral. Of course, the solution to this is natural log. So the potential difference is lambda over 2 pi epsilon naught times the natural log of B minus the natural log of A, or better yet, the natural log of the ratio of B over A. If we want, we can replace lambda. Say our Gaussian surface might have a length lowercase l, but our whole cylinder has a length capital L, and the total charge, if we shade all of it, is capital Q. So delta V is equal to Q over 2 pi epsilon naught L times the natural log of B over A. So our third step capacitance is equal to charge times the inverse of the voltage. So capacitance is equal to Q times 2 pi epsilon naught L over Q times the natural log of B over A. Q cancels out, and the capacitance for the cylindrical capacitor is 2 pi epsilon naught L divided by the natural log of B over A.